Welcome to the second lecture on actinides. So in the previous lecture, we have discussed about the actinides and why it is important to study the chemistry of actinides, and also some of the man-made actinides. I have given a detailed account of neptunium and plutonium synthesis. Now in this lecture, we talk about some of the other aspects like actinides in nature. So though thorium, protactinium and uranium are available in the nature in large quantities, some of the other actinides which are also available in nature in very, very trace levels are actinium and plutonium. It is surprising that plutonium also is available in ultra trace levels. As discussed in the previous lecture, this plutonium comes from some of the fission reaction taking place in nature, where in the very large deposits of uranium is there in the uranium mines, like the Oklo phenomena, where the mine in Gabon, Africa. Now, there, as I have already discussed, fissile content of the uranium was very high. Now, in earth crust, at this moment, we have around 0.03% uranium, average value I have given here. And in seawater, uranium is 3 ppb, it's very, very low concentration of uranium. Nevertheless, it's a rich source of uranium if somebody can really tap uranium from the seawater. Now, compared to uranium, thorium concentration is much higher in the earth crust. So thorium in earth crust is around 0.1%. But in the seawater, thorium content is very less. It is probably because of the hydrolysis of thorium, which is existing in the tetravalent oxidation state. Now, coming to the natural uranium, we have the fissile content, that is 235 uranium, is 0.72%, and other uranium sources also can be defined here as depleted uranium, where the fissile content or the 235 uranium is less than 0.72%, low enriched uranium 0.72 to 20%, 235 uranium, highly enriched uranium 20 to 90%, 235 uranium, and the weapon grade uranium is greater than 90% of 235 uranium. As I mentioned, this 239 plutonium, which is very ultra trace level, is reported in this uranium natural reactors, that is the Oklo phenomena, where the 235 content at that stage when this reactor was suggested to be operative was more than 3% 235 in the natural uranium in the mine at Oklo. Now 244 plutonium was detected in rare earth mineral bastnasite in also very, very minute concentration, that is 1 part in 10 to the power 11. Now some of these other actinides like protactinium 231, this can be formed by some of the reactions as is written here. Similarly, 226 radium, which with a subsequent neutron capture, it gets 227 radium, and the 227 radium can go to 227 actinium. So this is how actinium 227 is formed, and this protactinium 231 is formed from thorium 230, which by neutron capture it goes to 231 thorium, and then 231 thorium decays by beta decay to 231 protactinium. So this is how protactinium is formed, and also actinium is formed, 227 actinium. Another isotope of protactinium which is very important is 233 protactinium. It is obtained by irradiating 232 thorium by neutrons, and you get 233 thorium, which has a 22.3 minutes half-life, and by beta decay it gives 233 protactinium, which again another beta decay it gives 233 uranium. 233 uranium is very, very important again for reactors which are operating on uranium 233 as the fissile material. Now when this reaction is taking place, there is also the possibility of uranium 232 formation, which is formed by different reactions as given here. Like from 232 thorium, it can form 233 protactinium, which by beta decay goes to uranium 233, as I have already mentioned. But this 233 uranium can also undergo a N2N reaction to give 232 uranium. Alternatively, we also can have this protactinium 233, the same reaction, but instead of decaying, before decaying to 233 uranium, it can also undergo N2N reaction to give 232 uranium. Thorium 232 also can undergo N2N reaction, and it gives 231 thorium, which by beta decay gives protactinium 231, and which can capture a neutron, and by N gamma it goes to 232 protactinium, which undergoes beta decay to give the 232 uranium. So this is how actually this uranium 232 is formed in a rather small quantity when producing this 233 uranium. But it is very important because this uranium 232 has to be removed from the uranium 233, otherwise the operation becomes very difficult. As you can see from this decay reactions shown here, from uranium 232 goes to 228 thorium, then 224 radium, 220 radon, 216 polonium, 212 lead, and these are all by alpha decay, and then 212 lead by beta decay it goes to 212 bismuth, which undergo another alpha decay to give 208 thallium, which is a very hard gamma emitter, and this gives significant dose to the working personnel. Now, as I mentioned, this other actinides also can be synthesized in the reactor by neutron capture. We have just mentioned about how protactinium is formed in the reactor. Also, I will show here how neptunium 239 is formed in a reactor by irradiating 238 uranium by a neutron, which produces 239 uranium, and it undergoes a beta decay to give 239 neptunium, which has 2.3 days half-life, and it is converted to 239 plutonium again by a beta decay. This plutonium 239 can undergo alpha decay to give 235 uranium. So this is the general decay series of this 238 uranium if it is undergoing a neutron capture. Also, this 238 uranium can undergo neutron capture to give 237 uranium by a N2N reaction, and which again decays by beta decay to 237 neptunium. 237 neptunium is very, very important because it has a very long half-life, and once it is produced in the reactor, it goes to mostly to the waste as a minor actinide. It has a very significant repercussion in the radioactive waste management because of the very long half-life of 2.1 into 10 to the power 6 years. 237 neptunium is also produced in the reactor by 235 uranium capturing a neutron, giving 236 uranium, which is another neutron capture, gives 237 uranium, and by beta decay it gives 237 neptunium. So these are the ways this 237 neptunium is produced. Also, some of the relatively heavier actinides like americium and curium, they are also produced by again neutron bombardment, like 239 plutonium. With 4 neutrons it gives 243 plutonium, and then by a beta decay it gives 243 americium, which can capture a neutron to give 244 americium, and which again undergoes beta to give 244 curium. So this is how americium and curium, these are also produced in the nuclear reactors. Now for high yield, we need actually high neutron flux. As I have already mentioned in the previous lecture, this thermonuclear explosion, it was taking place and there we have detected Einsteinium and fermium. That is how these elements were discovered. And also, if you take 239 plutonium and you irradiate in a reactor with a very high neutron flux, like 3 into 10 to the power 14 neutrons per centimeter square per second, then you need a very years of irradiation for producing even 1 milligram of californium 252. I have given here some of the actinides which are produced in a reactor by irradiation. You can see that 248 curium, this is formed with 150 milligram 248 curium is formed, and 249 berkelium is formed, only 50 milligram under the same conditions, and 252 californium you get 500 milligram, 253 Einsteinium only 2 milligram, and 257 fermium only 1 picogram. So this is because of this reaction cross sections are also less, and also the T half of this radionuclides of the actinides, you can see here, it is very, very less. So that is how it is decaying also. For 248 curium, it was 10 to the power 5 years, whereas for Einsteinium it is only 20 days, and for fermium it is only 100 days. So that is how it decays also, the heavier actinides, and the amount also is less because of the very low neutron capture cross sections. There are also these actinide synthesis can be done by charged particle bombardment. For example, 238 plutonium is synthesized by deuterium bombardment of 238 uranium. The reaction is given here, where take 238 uranium and with the deuterium you get 238 neptunium, and this 238 neptunium undergoes a beta decay with a 2.1 days half-life to 238 plutonium. This is a reaction actually which was used, as I mentioned in the previous lecture, for plutonium production for the first time in the Berkeley Radiation Laboratory. Now similarly, this californium also can undergo a charged particle bombardment like 11 boron 5 plus with this ion beam. If it is bombarded, then it gives 256 lawrencium and also 4 neutrons are emitted. This is how the heavy actinides and the transactinides are made by the bombardment of charged particle. This will cover in a more detail when we are discussing about the transactinides. Now I will summarize here this heavier actinide elements synthesis by accelerators. So what we do is these accelerators, they should have good beam current and high energy charged particles are needed. The product many times is contaminated by the fission product. With the fission reaction will be taking place to a much larger extent than this production of the heavier actinides. So that is how this separation of this heavier actinides from the fission product is required. Also, if you go to very heavy actinides or even transactinides, their atom at a time scale, these elements or the nucleides are formed. So that is how these continuous experiments are needed. If you want to carry out some of these experiments, particularly the chemistry experiment, online experiments has to be done when these experiments at an atomic time scale, these actinides are produced, and this has to be transported to the adjacent laboratory where this experiment has to be carried out. And there it is continuously these experiments needs to be carried out because otherwise they are decaying. And this identification is done by parent, daughter and the granddaughter correlation, where you have one particular actinide A which is decaying to B and which is decaying to C, and A, because of it has a very short half-life, when you carry out the experiment you cannot probably see A, but B and C will be in significant quantities. So by detecting B and C, you can always say that well, A has also formed, and that is how the chemistry of A has been established. The products are also highly radioactive because of their very small half-lives, and because of that the solutions are damaged due to radiolysis. These have very high radiotoxicity, and also because of this remote handling is a requirement for this type of experiments to be carried out. Identification, as I said, it is difficult because you have a host of fission products also are formed. So identification is difficult, and you need to separate from the fission products and then identify these radionuclides. The products also have a very low stability, as I have already mentioned, nobelium isotope. As you can see here, even nobelium with a half-life of 1 hour or lawrencium with a half of 3 minutes, they are isolated, but then because of the low stability, we have to carry out the chemistry very, very fast. Now coming to the position in the periodic table, in the late 1930s, only 4 actinides were known, that is the actinium, thorium, protactinium and uranium, and the last 3 were placed in the periodic table as another transition series, that is the 6D transition series, as the homologues of hafnium, tantalum and tungsten. Now, as I have already mentioned in the chemistry of neptunium, how the neptunium was placed under rhenium. So because of this particular positioning in the periodic table to the 6D transition series, this was suggested that time. However, the quantum theory of Bohr and other experimental results suggested that these actinides, instead of being the 6D series, they may be the 5F series. And also the inconsistency between the theory and chemical properties made it difficult in placing them in the periodic table. So there were a lot of confusion. I will be showing in the next slide how this confusion was actually cleared. Then Alfred Werner in 1905 suggested that thorium as the homologue of cerium, because thorium and cerium, their chemistry very much comparable, and he sowed the seed for a new series like the lanthanides. After the discovery of neptunium and plutonium, and based on their chemical properties, their placement in the 4th transition series was challenged, and it was concluded that neptunium and plutonium, their chemistry is more similar to that of uranium rather than that of rhenium and osmium. So after the discovery of americium and curium by Seaborg's group in 1944, the similarity between lanthanide and actinide was recognized because americium and curium both behave as trivalent metal ions, and the similarity in the spectroscopic and magnetic properties also was due to the similarity in the electronic configuration. I will be discussing the electronic configuration shortly. Similarly, in the crystallographic properties, owing to the near matching in the ionic radii of these actinides to that of the lanthanides, also suggested that they may be similar to the lanthanides. Oxidation states, however, are not similar to that of the lanthanides, like thorium, protactinium and uranium. They are not tripositive in solutions, but they are +4, +5 and +6 oxidation states are formed in those cases. Variable oxidation states for the early actinides also have been detected, but then the reason for this will be because of the 7s, 6d and 5f energy levels are very close in the energies. So that is how the variable oxidation states of the actinides were explained. Now, as I was mentioning, there were a lot of confusion actually about the 5F series before the 1940s. So this is some of the, I'll list down how these different groups they were proposing where the 5F series will be. 1913, Rydberg proposed that the transition groups should be there around uranium with 5 of electrons being filled. So a lanthanide type of series, but beyond uranium. In 1923, Bohr suggested that 5F series should start with element 94. And in 1924, Goldsmith, he proposed that up to 96 should be homologue of the platinum group, and beyond that only you can have the 5F series. In 1926, Sugira and Virey, they have done calculations and indicated that the first 5F electron entry should be for element 95. In 1933, Hu and Goldsmith did more refined calculations and suggested that the first 5F electron filling should be not for element 95 but for element 93. In 1926, Macmillan, Mawley and Smith, they have suggested that the 5F cell should start with thorium, and in 1926 again, Swayne, he suggested that 5f electrons should start with protactinium and uranium. In 1934, Saha and Saha, they suggested the 5f electrons should start at thorium. And in 1930, Karapetov suggested the first 5f electron with element number 93. So as you can see here that many people suggested that it should be at 93 or 94 and some even 95. Subsequently, 1928, Van Gross suggested that again it will be starting from element 92, that is uranium. And 1938, Quill suggested that it starts from 95 or 99. So he has increased to the heavier actinides. 1937, Goldsmith changed his original view and based on the crystallography work suggested that the 5f electrons enter from protactinium or maybe thorium or uranium. So he suggested the name actinide and also he suggested other alternative names like thoride, uranide or protactinide. Now, what is the major objection coming? That this neptunium and plutonium, they behave like uranium and thorium, but not like rhenium and osmium, which is there in the periodic table for the 6D series. Now there is no evidence for the volatile plutonium tetroxide in contrast with the volatile osmium and ruthenium tetroxides. And also there is no evidence for an oxidation number of 8 in case of plutonium. So these suggested that this plutonium is definitely not behaving like osmium. The observation of Zachariasen of the isomorphism of the compounds, this thorium dioxide, uranium dioxide, neptunium dioxide and plutonium dioxide, they found that it is not isomorphic, uranium dioxide is not isomorphic to molybdenum dioxide, and his observation of the regular decrease in the radius of the metallic ion in these oxides also suggested that this is a separate series similar to the lanthanide series. Other evidences are the magnetic susceptibility of uranium and plutonium, sharpness of the optical absorption of uranium and plutonium, evidence of organic complexes of uranium 4 plus and plutonium 4 plus. Also, the analysis of the spectrum of the uranium atom come to the conclusion that the electron configuration of the lowest state of uranium is 5f3 6d7s2 with the term symbol 5l6. Similar to the lanthanide series, the electron does not go to the 6d orbital but to the 5f orbital. Now the plus 4 state was prevalent for thorium, uranium, neptunium and plutonium, the last three under the reducing condition, and also plus 3 state was also reported for uranium, neptunium and plutonium under the suitable reducing conditions. Actinide series differed from the lanthanides as the higher oxidation states prevailed in case of the lighter actinides, and thorium behaved like cerium as both have the plus 4 oxidation states. Now with this background and also the discovery of americium and curium by Seaborg and their chemistry studies suggested that they were more like the lanthanides rather than like the transition elements. So Seaborg was tempted to propose this actinide concept and he has sent a publication that time suggesting his actinide concept, and his colleagues they advised against this because he said that this is a very wild idea. You cannot have a actinide series similar to the lanthanides as Seaborg was proposing. They said that your reputation will be ruined, but Seaborg said that I didn't have that much reputation at that time and I was also more fortunate that I was right. Ultimately, he was proven right that there was an actinide series similar to the lanthanides. Now, coming to the position in the periodic table, as I have mentioned before, the actinides initially are proposed to be under this fourth transition series. It was proposed. However, after Seaborg's proposition, this was the actinide series where thorium is also just below cerium and protactinium below praseodymium. However, this behavior of the lanthanides was entirely different because they are all plus 3 oxidation state, and for actinides only beyond americium you have the plus 3 oxidation state. Now coming to differences between the actinides and lanthanides. Lanthanides are naturally occurring except promethium, and actinides are man-made except for actinium, thorium, protactinium and uranium. And there is a difference in energy between 5f and 6d orbitals of actinides are less than that of the 4f and 5d orbitals of the lanthanides. 5f orbitals of the actinides have greater spatial extension and hence participate in the bonding. Some cases even covalent bondings are reported for the actinides, and that is the basis of the lanthanide actinide separation, which I will be discussing in a future lecture. Now coming to this electronic configuration of the actinides, I have shown here this from starting from actinium to lawrencium. You see the electronic configurations, and also I have, for comparison purpose, I have put the electronic configurations of the lanthanides. You can see here that for lanthanides, only for cerium, gadolinium and lutetium, you have the d electron, and for all others, you find that the f electrons are getting filled. On the other hand, for the actinides, you see that the initial actinides up to neptunium, you have the d electrons are also there, and also the f electrons are also there. Now, beyond neptunium, you have this plutonium and americium. There you do not have the d electrons, and apart from curium, you have all other actinides again with only the f electrons getting filled gradually. So this is a similarity of the actinides with the lanthanides starting from plutonium, but the early actinides, as I have already mentioned, because of the comparable energy levels of the 5f, 6d and the 7s levels, so that is this type of configurations are possible. Now coming to the electronic configuration, also here you can see I have given this figure where you see that this comparison of Fn-1 ds2 and Fn ds2. These two electronic configurations are compared. As you see here, Fn-1 ds2 is more stable up to the element number 93, that is neptunium, and beyond that, like the plutonium, you have this Fn ds2 type of configuration is there from plutonium, and then americium, and up to curium again you have this Fn-1 ds2 type of configuration, and beyond curium again you have this configuration where you have Fn ds2, which is more stable. So this is what I would like to cover here in this electronic configuration, and we'll discuss more about this chemistry of actinides in the subsequent lectures. Thank you.